video provides an overview of structural vibration, examining both free and forced responses, and outlines strategies for effective vibration mitigation. Free vibration in a structure takes place following an initial disturbance without the influence of any continuous external force. The motion during free vibration is transient and decays with time. The frequency and decay rate of free vibration is dictated by the intrinsic properties of the structure, i.e., stiffness, mass distribution, and damping. Structures vibrate with different patterns of vibration known as modes of vibration. Every mode of vibration has its own distinct natural frequency. When a structure is perturbed at one of its natural frequencies, it vibrates with the particular pattern corresponding to that frequency. Every mode possesses its unique damping level, influencing the duration and rate at which vibrations persist or diminishes after the cessation of perturbations. When a structure experiences a sudden and impulsive disturbance, like being struck with a hammer, multiple modes within the structure initiate vibrations at their respective natural frequencies. Due to the brief duration of such disturbances, the resulting vibration in the structure is classified as free vibration, which is transient and diminishing over time. Many structures lack sufficient damping, meaning they have limited capacity for energy dissipation. This deficiency leads to prolonged decay times for vibrations to cease. Essentially, the vibrations persist for an extended duration, presenting challenges in vibration management. Introducing additional damping facilitates rapid dissipation of vibrational energy, contributing to a quieter and more controlled structure. These three traces show the acceleration of a 1 degree of freedom structure with 3 different levels of damping. When a structure is subjected to a periodic perturbation, it vibrates harmonically in a sustained manner for as long as that force persists. This sustained vibration occurs at the same frequency as the forcing frequency, leading to a scenario where the structure's vibrations align with the frequency of the external perturbation. Examples of such perturbations are vortex shedding caused by wind passing around a tall structure, inducing lateral vibration into that structure, and rhythmic human activities on a floor system, inducing floor vibration. When the frequency of a repetitive external force aligns or comes close to one of the natural frequencies of a structure, resonance occurs. At this point, the structure starts vibrating excessively. Initially, as the perturbation begins, the vibration within the structure also starts. This vibration gradually builds up until it reaches a steady state level where the amplitude of vibration becomes constant. During this steady state resonance, as long as the external force's severity remains consistent, the structure continues to vibrate at this heightened level. This sustained and excessive vibration at the resonant frequency is a critical characteristic of resonance and can cause significant issues or possibly structural failure if not addressed. The frequencies of resonant vibration are called resonant frequencies, which are almost the same as natural frequencies in structures with low damping. When the external force causing resonance ceases, the structure doesn't immediately stop vibrating. Instead, it enters the free vibration phase, during which the structure continues to vibrate, but in a decaying fashion. This demonstration illustrates the buildup of resonant vibration, followed by the lingering decay of free vibration in a structure with low damping. The frequency response of a structure describes its reaction or behavior when subjected to periodic perturbations at various frequencies. It essentially outlines how the structure vibrates in response to harmonic inputs at different frequencies. Typically presented by a graph, The frequency response curve showcases the structure's sensitivity to different frequencies, indicating which frequencies it amplifies, attenuates, or maintains unchanged. This figure shows the acceleration over force frequency response functions of a 1 degree of freedom structure with 3 different levels of damping. The following observations can be made by looking at a frequency response graph. 1. Resonance occurs when the perturbation frequency aligns closely with the structure's resonant frequency. This leads to heightened vibration, which is depicted on the graph by a peak at the resonant frequency. This severe vibration can cause significant issues if left unchecked. 2. As shown on the graph, increased damping in a structure results in a shallower peak at the resonant frequency. In other words, structures possessing increased damping exhibit less pronounced resonant vibration. For instance, raising damping from 1% to 11% leads to a roughly 20 decibel decrease in magnitude, indicating a tenfold reduction in the severity of vibration. This demonstrates how damping effectively controls and reduces resonance. 3. While damping effectively tames resonant vibrations, it doesn't notably impact the structure's response at frequencies away from the resonance point. This means that damping primarily targets and mitigates the severe vibrations at the resonant frequency without significantly affecting vibrations at other frequencies. Frequency response is crucial in understanding, designing, and/or modifying structures to ensure proper vibratory attributes across frequency spectra. Structures are most prone to severe vibration or resonance when they're disturbed at or close to their resonant frequencies. To mitigate resonance, one can either modify the structure itself, introduce damping to it, or employ a combination of both strategies. These approaches aim to either shift the resonant frequencies away from the perturbing frequencies or dissipate the vibration energy. Modifying a structure can involve increasing its mass or its stiffness. In most cases, increasing stiffness is preferred and can be achieved by welding additional steel onto the existing framework. For instance, welding T-sections beneath existing W-sections in a floor system or introducing braces to industrial support structures are common methods. However, modifying an existing structure comes with its challenges. Issues like disruptions for occupants, restrictions on welding, and the potential for lengthy implementation periods can arise, making the modification process complex and sometimes less feasible. Stiffening and adding mass don't directly dissipate vibration energy within a structure. Stiffening raises the resonant frequency, while adding mass lowers it. These structural modifications create a mismatch between the structure's resonant frequency and the perturbing frequency, effectively preventing resonance from occurring. The primary aim is to avoid resonance rather than dissipating the vibration energy. Damping, on the contrary, aims to dissipate vibration energy within a structure. This involves integrating specific damping devices into the structure's composition. Various mechanisms such as viscous, viscoelastic, magnetic, and friction are employed in making dampers. Dampers are two-point devices. They not only connect to the vibrating structure at one end, but also require anchoring to an abutment at their other end for effective operation. In certain applications, like when dealing with vibrating pipes at elevated levels or bouncy floor systems, there might not be a support structure for dampers to attach to. In such cases, tuned mass dampers serve as an alternative. These single-point damping solutions don't require anchoring points. They are tuned devices targeting a single mode of vibration and effectively adding damping to it. In applications where strict vibration standards must be met, a blend of solutions could be necessary. For instance, in the scenario depicted in this image, the vibration levels in a medical facility operating room floors were reduced to meet specified standards. This was achieved by reinforcing certain beams to add stiffness and strategically installing tuned mass dampers beneath the floor system to add damping to it. Structural vibration is a crucial aspect in engineering and construction, as excessive vibrations can lead to structural damage, discomfort of the occupants, and even compromise safety. Structural control involves the implementation of techniques and technologies to mitigate or manage these vibrations. DEICON employs various methods such as viscous damping systems, tuned mass dampers, as well as semi-active and active control systems to reduce vibration and enhance structures' serviceability and longevity.